avoid the every problem's a nail approach. So he's having this hammer and trying to hit nails, but rather try to talk to people and then figure out. I mean, this has been my entire philosophy to research since I became a faculty member. Is like, you got to talk to people who aren't in my area, figure out what problems they're dealing with, and then figure out how to apply what I know to their problems. And of course, 99 times out of 100, I can't, right? But you can find these interesting ones. You're like, and that's the key. Is just talking to lots of people outside of our research community, and then you can, I think, find ways that if you've mastered a few tools, you can find ones that you can adapt these tools and do something non-obvious that hopefully brings insight to their problems. Okay, and I think if you look at the most impactful recent work, they either stem from a back-to-basics approach where we rethink assumptions that were thought to be sacred, or they look at new commercial applications that are changing the problem in a new way. Okay, Hesham's and Alex's work, for example, were of this type, as Yuri's work on short channel coding was more of this type. Okay, and I think I've hammered this point along. So this concludes my talk. And I hope, I approach this with humility. This is a very hard topic to speak about. I hope it just starts some conversations.
Okay, thank you very much. Questions? I have one question.
Okay.
Shannon is well known for his master thesis also, right? Connecting Boolean algebra and switching. He's less known for his PhD thesis. And you talk about the genomics and information theory. So is the PhD thesis of Shannon was in genomics, right?
I actually didn't know that.
Yeah, he did work in counting DNA sequences and things like that.
Okay.
So his work was in genomics. But not many people know that. So that was a question. Do you see the
that's actually interesting. You can count me as one of the people who didn't know that. I guess I mostly know his work, from Bell Labs. Of course, I know some of his switching and Boolean logic work, But I did not actually know that. It's very interesting.
Yeah, I don't know. I didn't go through the work, but is there a connection with information theory? Because there should be a connection with information theory. I don't know. Somebody read the thesis of Shannon, PhD thesis.
I'll have to add that to the places to start, along with.
Okay, that was one question. Another question, please.
Andrew.
Yeah, Andrew.
I want to ask a question about the content hashing. Content hashing.
Yeah.
I found your talk very good at summarizing the main ideas and the intuitions for this problem. So for content hashing, are you able to explain intuitively why the hit rate is so high? Because predict feature, as you said, is difficult.
Yeah, so it's a combination of prediction and even more than prediction, though, is training. So this isn't really an information business, but it's actually training people to realize that they want to load the cache content. So for example, Hesham's, how his product works and how he's getting such a high hit rate is you download his app and then it connects to a bunch of apps. And so for example, when I open CNN, it'll show a little logo, like his logo app next to the cache content. And so then people learn that if I hit the cache one, it comes up immediately. So I hit the other one, and I sit there for 30 seconds while it loads. And so you can actually, by predicting what they might be interested in, and then actually they will choose on their own volition the cache content just because it's going to result in a better experience for them. So that's I think the magic sauce. You can actually train people. Okay. So that's the reason it's hit rate so high.
So it's caching ahead of like for 2 seconds or 2 minutes.
Yeah, I think it's almost like pre-fetching. Okay. Yes, it's as much pre-fetching as caching. In fact, they don't do it even more than a day ahead of time. So like during the night, they'll download a lot of stuff that they think people are likely to look at, like the most popular videos from yesterday or ones that are training.
Okay, thank you.
Yeah, just this may be an odd question, and there may not be an answer to this, but if the root of zeros and ones was not the root that was taken, and something in between was also a state that was available, like is being proposed in the world of quantum electronics, like is a proposal for rebooting computing. How would things, what would be your view on if things could be very different then?
I think they are. I mean, this is the field of quantum information theory, right? Where you don't have a 0 or 1 state, but rather a probability or such a state, right? I'm not an expert in that area. hopefully, is there anyone here who's an expert in quantum information theory? Wants to speak to how kind of this is a subfield of information theory, but I just don't feel I have an expertise to that is an interesting thing, because that is obviously a lot of, excitement there, looking forward 20, 30 years, building computers to be super, super dense, and would you give up the certainty of being a state?
Okay, more questions? I saw, yeah.
That question you made, it's a prediction. When you predict in March what people want to say.
Yes. Yeah, so it's a prediction, but I mean, if you look at, for example, some of his theoretical papers, it's about, how much you widen the window, how much can you, at least in theory, gain, given certain statistics for the network congestion. But it is, as I mentioned in Andrew's question, it's a combination of prediction and training. So prediction's hard, and I think what I really like about Hesham's approach for his company is that you can actually train people as well. So yeah, if you're just trying to, out of the universe of YouTube videos, predict what people are going to want that day, you're pretty hooked. But I mean, I think we all have had the experience where we open Netflix or YouTube and you just sort of pick whatever's interesting on the first page and click that, right? And this is certainly what. So if you can cache those and then just put the cached ones on the first page, you can kind of. Most people are sheep and don't know actually what they want to view, and they'll just view what's there.
Which means that later on in the future to communicate, if you know what you want to say, what you can say already.
Yeah, I think everything's perfect issue pretty much.
More questions? I have a remark on your committee that your members were all from the US, right?
They're all at US universities.
Yeah, but if you look at information theory, there was a parallel development in Soviet Union. That's
true.
And also, I think after that, there was a development in Asia, like in Japan. They had their, I would say, their own information theory, and also in parallel to the Western information theory. But it might be a pity that these contributions are not in this list.
Yeah, I think like I said, we sort of I think to do this report truly right would be a massive undertaking. It would take a year or so, and would I think so. We want to do something. I guess we started with a little bit less ambitious goals, but I think indeed that's one of the reasons we didn't put in citations, because it'd be impossible to fairly give credit to different.
Yeah, but it would be interesting maybe to make a report. I don't know whether in Japan, in Saita, you're interested in producing a parallel report on the developments that you have in Yukon. Sorry?
Yeah, we would do that.
You will do that?
Yeah.
Okay. That's good news.
Yeah, this is by no means the last word. I think we called it a perspective because it's you can get 20 different committees and have 20 different reports. But I think most people would hopefully recognize the breadth, right? That this is becoming broader and broader, and but there's still some sort of core to the information theoretic approach that makes it.
Yeah, but we should not think that information theory is only US based. That there's,
of course not. I'm sorry if I give that impression. That's definitely not my impression.
No more questions. Remark? I have one question. Another question. That if you do the networking area, I think Gallagher had an important contribution there.
Yeah.
In bouncing protocol information. Right?
Yeah, that's.
And then I saw your models of the access and the broadcast channel. Isn't the statistics of the source hindering, bothering the development of information theory in networks?
Well, okay, so I mean, when I think of Gallagher's paper here, this is where he tried to bring together sort of queuing ideas and delay with capacity. This is very hard. So I guess with the MAC and broadcast channels, we're still looking at sort of instantaneous communication. So I don't know.
Because in information theory, you assume that the sender always wants to send something, right?
Yes, that's true.
And
that's
in
true.
practice, you don't have it.
Yeah, that's right. So this is like, there's some sort of a scheduler behind this that ultimately then picks K users that get sent. Yeah, that's true. Yeah, this is one other hard thing I didn't even touch on that makes the networking hard for.
Okay. Well, then let's thank the speaker again. So if there are no announcements from the chair, I think we have coffee.
Ja, nou, it's now coffee breaks, tea break, whatever you like. and
Half an hour.
Half an hour tea break for the next session. Thank you, Jim.
Thank you.
Thanks. It's a tough topic, but it's very broad.
Proceedings of the IEEE in 2011. You also find this reference in the booklet that you have together with the abstract. So if you want to have a good introduction to this topic, please have a look at this paper. Okay, so the technique was proposed by Boba Ganase and Michael Gaspar, and it exploits two properties of the wireless medium, the broadcast and the superposition phenomena. So this is what I will focus on. We are going to look at both these properties to see how it can have some certain benefits. And the technique is also known as reliable physical layer network coding. So before going into this technique, it may be good to first review a little bit of the basics of network coding and then make the step to reliable physical layer network coding. Okay, so here's the network coding paradigm, as it's called. So it's additional routing solutions for communications. Then mostly independent data streams are kept separate. We try to avoid that they are meeting the same frequency or the same time slot or whatever. So we try to keep these sequences separate. With network coding solutions, we are going to allow nodes in the network to combine independent data streams. And I will give a very simple introductory example to give you the main idea about this. So the example which I will use is that we, Jasper and I, are going to exchange pictures, but we do not have a direct connection. We do that via a relay. First, let's look at the traditional approach to do so. So I upload my picture to the relay, and then I continue. The relay sends it to Jasper, and the other way around, Jasper uploads his message to the relay, his picture in this case, and then the relay forwards the message to me. And then we have exchanged our pictures, and we see it takes 4 time slots if we do it like this, or 4 rounds of communication. So, okay, now let's look at the network coding approach. The beginning is the same. I upload my message, but the relay does not forward it. It waits for Jasper's message, so it has 2 pictures of us now in its possession. And this relay has this broadcast property that it can reach both me and Jasper in the same time slot. And what is done here is we are going to take the sum of these 2 pictures, then we get something like this. This could be a figure from a horror movie or so. But
That's good.
then we have this situation. Now what can we do? So we get this strange picture, which is actually let's say in this case the binary addition of the 2 pictures. And now note that this picture was composed by the sum of our 2 pictures. So I can decode because I still have a copy of my own picture in this example. So if I subtract that picture from the one that I received from the relay, I get Jasper's picture. And Jasper can of course do exactly the same thing. Jasper also gets the same picture, but he subtracts his own picture, and then he gets my picture. So this is just of course a very simple example, but it gives the key idea of what network coding is about. You get the sum in this case, or a linear combination of messages, and then by doing here a simple subtraction operation, but in general it could be solving a system of linear equations, you can retrieve the original messages. So that is the basic idea of network coding. Okay, so let's look at some of the features. So we are going to transmit not the packets themselves, but mostly linear combinations of such packets. So you can write in such a way where the xi's are the packets of the various sources. Alpha I are some coefficients. In the previous example, I just took them 1, right? I took the sum, but it could also be other coefficients. And then all our calculations are done over some finite fields GFQ. Some advantages may be higher throughput, lower energy consumption, right? As we was already illustrated a bit in the previous examples. Of course, there's also some disadvantages, right? You should not only look at the bright side of the story, but also some disadvantages. Processing is required at this relay node, relay node, we need to do some operations. We need to solve a system of equations at the receivers. Synchronization may be more important here than in the other way of communicating. So there's also some drawbacks. basic idea of network coding. Now let's look at this from another perspective. So this is more or less the same example as we had before, but now with the messages here are indicated by M1 and here by M3. So the 2 is the relay, 1 and 3 want to exchange messages. So this is exactly the example as I had with the picture. This is then the solution with the network coding technique into the game. And then we need 3 rounds of communications, as I said. That is exploited in broadcast. And then a couple of years ago, people came up with the idea which goes further, which is known as physical layer network coding. And there it was asked, well, what we can do here in 2 separate time slots, maybe we can do here in the same time slot. So both user 1 and user 3, they upload their message to the relay in the same time slots. And of course, people immediately shout, yeah, but there's interference, right? They are at the same frequency, in the same frequency slots. Well, there will be something wrong there. You cannot recognize anymore what was going on. Right? So that has always been considered as something which is annoying, right? Something that we should prevent. But here we are going to try to exploit that feature. Now suppose that this works and that we have then here the sum of M1 and M3, then we could do the same thing as here, right? We again in one shot we broadcast then the sum of M1 and M3, and we can do the same game as before. So this would require only 2 rounds of communication. So it would exploit both the broadcast principle and the multiple access phenomenon. But of course, as I said, we should have a close look at what's going on here, right? Because yeah, this looks like something very tricky. But let's consider some properties of the wireless medium which give us some evidence that this could be possible. If you look at the wireless medium, then we see signal fading can be considered as a linear operation. If you look at the formula here, you see the fading coefficients, right? They are mostly multiplied with the transmitted signal. Signals interfere in a linear additive way. That is the sum here that you see. So we take a summation over the different signals over here. And the noise is independent of the signal and at the receiver, so mostly we model things that here the noise term is then added to this term over there. And that is what we receive as denoted by writing. So everybody is very familiar with these kinds of formulas. So this is a way to look at it. And now note the resemblance with what's happening in network coding. In network coding, as I said before on one of the previous slides, we take also a linear combinations of messages over some finite fields. So you see there's already some resemblance, and then we get rid of the noise. Maybe we can have the same game as we play here by the natural phenomena as they occur on the medium. So we have now a further paradigm shift, which we are going to explore. So we are going to consider interference as a friend and not as an enemy anymore. That is the basic idea actually. And so we try to exploit the broadcast and superposition principles. That is what we would like to do. And let's do a simple case study in order to give you some evidence that this is possible. Suppose that we have UI denotes the input bits, and let's first look just at the bit level. UI is the input bit from user I, and here we have 2 users, users 1 and user 2, and here in the middle is this relay. And once again, they want to exchange these bits. And we are looking here at a situation that we have an additive white Gaussian noise channel, and that we're going to use binary phase shift. So as usual, the zeros and ones from the input bits are mapped to +1 and -1 in the obvious way. And now note that the relay is interested in the modular sum, the modular 2 sum of S, which S is called S of U1 and U2, right? And what we observe, we assume that there is no fading coefficient here, right? It's just an additive white Gaussian noise channel. So what we observe is x1 plus x2 plus some value z, right? The noise term. Well, note that x1 plus x2 can have various values, right? If we take this kind of noise, it can either be 0, if one is +1 and the other is -1, and it can be +2 and it can be -2. But the important thing here is that if the sum is 1, then in both cases, either it's +1 and -1 or the other way around, it gives us a 0 here, right? While if the sum is 0, then it gives me either + or -2. So what I could do is, since we have this property, and since we know that the y is composed of this, we could take a simple decision rule here that if we decide that it's a 1, if the y is below a certain threshold, right, then it's close to 0, the absolute value of y, and then it's 0 otherwise. Right? Of course, by the standard techniques, you can easily derive this threshold, but we are details here, but from this it's clear, right? If there will be some noisy versions of this, so if it's close to 0, then it will probably be a 1. If it's away from 0, so it's either rather negative or positive, then it will probably be a 0. So that is the reason how we come up with this decision. And the sigma squared is, of course, the variance of this.
What is this?
Sorry?
What is this? Yes.
The S. Oh, sorry, that on the previous slide was introduced. S is the sum of U1 and U2. So we are interested in the sum of the two bits, which such as this, right? So 1 by U1 and the 1 by U2. And the relay should forward its sum of these two, right? So that is this S. So that is the parameter that the relay is interested in. And this is the decision that the relay takes. Based on the noisy observation, why it takes this decision, and then it can go. Okay, of course there can be errors in this vector, so this is how it could be implemented if you want to take into account that there will be errors, right? So during the first time slot, both users transmit their messages, so there's no longer considered bits, but a sequence of bits or other symbols, which is UI. Of course, it's modulated to a sequence XI, and this gives the relay access to the noisy sum of packets, as we saw in the previous slides. So what we now have here is, because we get then something called U1 plus U2 plus an error vector E, right? Like we always have in communication. And then during the second time slot, the relay broadcasts this, what it has decoded here to both users, again in a modulated version of course, and then each user retrieves a possibly corrupted version of the other user's message. Okay, now applying an end-to-end error correcting code over this whole thing, then we can get rid of these errors here and we could communicate reliably.
So you change the alphabet of the channel in this way.
Excuse me?
You change the alphabet of the channel.
In what sense?
Because it's binary, U1 and U2, and the relay sends the sum of the two.
Oh, no, sorry. The U1s, maybe I did not express that clearly here, but U messages are first transformed into X messages, right? In plus minus 1 sequences again. And then the noise is added, and then they are decoded into a sequence like this, and due to the fact that, as I showed on the previous slide, that if it turns out that this could go wrong, right, if you are, then such an error occurs on, let's say, the binary level. Yeah. Okay, this is not how it's done in the technique that Michael Gaspar and Bobak Nasa proposed. They proposed a technique which is called reliable physics of the computer forward technique. So we are going to exploit broadcast, and we are going to exploit the superposition principle so that we can try to have benefits from it. And what I will now present in the rest of the talk is some of the recent research results we have obtained with this group of people which I introduced on the first slide, to give you some flavor of what could be achieved with this. I won't say in a practical context because we still use rather abstract models, but I hope it gives you some flavor about certain some of the benefits which it could have. The first, I will further focus on throughput benefits in the context of multicast traffic. Here you find two papers which were presented at ISIT in 2013 and a communications letter which appeared in 2014. Once again, these references are also available in the abstract that you have in the book. So in this work we studied multiple unicasts, which is known as a very hard problem. So multiple unicasts means that we have point-to-point, not point-to-point communications, but two users sending messages, either the one to the other or both directions. But let's focus here on the situation. One is sending to another user, and then somewhere else in the network there's another pair, a source-destination pair, and let's see what we can achieve in such a situation. Well, we do a lot of assumptions here, as indicated. We assume a network with local interference, half duplex, time is slotted, links with unit capacity. The number of unicast sessions will be denoted by K, and we will assume the situation that we have a common rate for all sessions. So all these sessions, they communicate at the same rate. We're going to make all kinds of variations of that, but these are the assumptions that we do. Now let RTR here denote the maximum achievable common rate in traditional routing modes, right? So just as the first example. And then let's RCF denote the maximum achievable common rate in computer forward modes. So where we exploit this broadcast superposition principle. And then the improvement factor I is defined as the ratio of these two, so RCF Now our main result, which I will illustrate a little bit, is that this factor I is at most in the order of k, so linearly k, for any network. And furthermore, we will show a gain in that order that is indeed achievable for some networks. So this says something like upper bounds. Well, I can never be more than something in the order of k, but we also show the other way around. There exist networks for which this order of k can be achieved. Okay, let's see how this works. I will give you some idea, a sketch of the proof. So here you see some network. It could also be a beautiful stars formation, which we can see here on the southern hemisphere tonight, maybe again, right? But in this case, just look at it as a network with nodes. And here you find with S1 is the source for session 1, and here you see the destination for session 1, and here you see the source for session 2, and here's the destination for session 2. So this source wants to send messages to this particular destination, and in this case there are 4 sections, right? In this example. Now let's first look at the, let's say, classical string. Then we have the traditional routing mode. Then we just find a path through this network, and we are forwarding the messages from this node to the node here, to the node there, etc. And now suppose that we have a situation that this node is transmitting, source 1 is transmitting to this relay node. This also implies that there's, at the same time, there's no communication possible here, because we assumed the half duplex constraint, right? We assumed that a node is either receiving or transmitting, so if this node is receiving, it cannot transmit. Furthermore, also, there can be no communication here on this link, because suppose that this node would be forwarding, right? Then it would interfere with what's going on here, right? This node would receive 2 signals at the same time. It would receive this signal, the desired signal, but also the signal from here. And in the traditional setting, that would cause an annoying effect of interference that we do not deal with, right? So we cannot handle that. So, of course, then next, this one can transmit again. If we are going to look at forwarding messages from here to there, this will not interfere with what's going on there. So this one can be used again. And this one, of course, cannot be used because of the same principle of the half duplex constraint. Well, in the next round of communication, the message which arrived here can, of course, be forwarded to the one over here, but for similar reasons as before. At the same moment, there can be no communications over here, but there can be communication there. And in the next round, we can have a message transmitted from the node here to there. And then we can go on again. Of course, we take the scheme from the first round. This one is transmitting, this one's transmitting. And so we can keep on forwarding messages from S1 to D1 in a round of 3 communication sessions, right? It's a session of 3 rounds. Okay. Now, if we're going to look, this reasoning which I just gave you gives us a lower bound for traditional routing. Because, as I said, I can, in this case, kind of achieve a rate of 1/3, right? We assume that, as we call it, I assume unit capacity for all these links. And I need every 3 rounds a link can transmit something. So this gives me the 1/3 here. And if I assume that I give different time slots to all sessions, which is not maybe the best solution, but here I'm just looking for a lower bound, a rather trivial lower bound. If I give different rounds to all sessions, it means that we can have a common rate on all these sessions of 1/3k. So the 3 I just explained, right? It's the round-robin system, and the k is then the number of sessions which I have. On the other hand, the upper bound for the computer forward technique, the trivial upper bound, because all links have unit capacity, so also at the receiving node I only have unit capacity there. There we have, that is can be at most 1. So we can get an upper bound, a very loose upper bound in most cases, for the improvement factor, that it can never be more than 1 divided by 1/3k, so this gives me the 3k. So here I have a result that the improvement factor can never be more than something in the order of k. Well, not such difficult proving technique, but this gives them a fundamental link. Now the other way around, do there exist networks in which you can achieve this? And that was the main result actually of the paper, that we have such a network. I agree with you, as you see it in a moment, it may in many cases not be the most practical network, but it gives evidence that big improvement factors are possible indeed. Here is the network that we are considering. Here we see nodes which act as sender. There are K of them. Here are the nodes which act as receiver. There are also K of them, right? And the corresponding thing here is that S1 here communicates with D1, S2 communicates with D2, sends a message to D2, etc. And here is a relay node which can be used for general purposes. So everybody can use it. Okay, now the strange thing of this network is that every sender node here is connected to every other, to every destination node, except the one to which it should communicate. Yeah? And every sender node is also connected to the relay node, and similar for the destinations here. You see that they are connected all to the relay, and they are connected to all senders except the one to which it wants to communicate. To look at it from another perspective, here is for KS3 what this looks like, right? So we see here that these nodes are on the circle and that we interchange senders and receivers, the destinations, and every node, sender node wants to send its message to a node which it has here on directly opposite to it. That is what we have, the situation that we have. Okay, you can. In a traditional routing solution, this is a very bad network because as soon as a node sends, for example, if S1 sends something to one of the other nodes in the network, it means that most of the other nodes should be silenced because the receiving node is also connected to these nodes, and then again we have this interference, right? These conditional signals, which in the traditional setting I do not allow. So here is some evidence that the traditional routing, the mode can be the rate can be at most 1 over k, because we have k of these sessions going on. And for example, if S1 is transmitting something to the other side, yeah, it cannot direct it to D1 as it should be, so it should take another route, maybe via D2. But yeah, if this is the desired connection, it means that all these nodes here cannot receive, because they will receive this message, which is not, the broadcast effect is not exploited. Also, the other option then is that S2 is transmitting to D1, but it should also be trafficked the other way around again in order to get it right, because in order to get the message from S1 to D1, we should have some loop like it goes from S1 to D2, from D2 to D3, and from S3 back to D1. Or you can use the relay, but in all options you can easily argue that the rate is at most 1 over k for this particular method. Okay, now the thing is that we have a network coding scheme based on this broadcaster superposition principles, which does the job in a very efficient way, and it works as follows. In the first round, all senders at the same time, they transmit their messages. So, according to the principles just explained in the introduction, it means that the relay here receives the sum of all these k messages, right? The destinations here, they receive the sum of all the sources except the one in which it's interested. So in the next round of communication, in the second round, the relay just forwards its message, the sum of all these messages, and it's then received by all these destinations. And then, for every destination it's clear what to do, it saves the result from the previous round, it gets here the sum of all sources, it subtracts the sum of all sources except the one in which it's interested, so then it has exactly the message in which it was interested. And once again, I completely agree with you if you say, well, this is not a very practical situation, right? No, this is indeed a theoretical case study which tries to see what could be in principle possible with this technique. And then we see that this example shows that since the rate in the TR mode, as argued, is at most 1 over k, and since we here, for the computer forward mode, we have a rate achieved of 1/2, we see that for this network, the improvement factor is at least 1 over k divided by 1/2. So 1/2 divided by 1 over k, so this is k over 2. And this is something in the order of k, right? So now we have the upper bound 3 over k, and there exist networks in which k over 2 is achieved. So this is the major result of that work which I cited in the slide before. Yeah, so this is what we have. So this gives some flavor about throughput. As I said, we also looked at energy benefits. This was presented at the Benelux conference, the local conference we have every year with information for you people from the Netherlands and Belgium. Also Luxembourg belongs to that, but we hardly have participants. Journal Jammer, by the way. We also looked at that. We have new results on that as well, which will be submitted soon. But in this work, it was the destination itself acted as the jammer. Well, in that case, we see here that what is received now here is the linear combination of H1 times XA, H2 times the jamming message, and of course noise. Then the relay can try to retrieve this linear combination of XA and XB, but it does not learn XA itself. And then of course it forwards this message to B. B gets the sum, and of course it can retrieve then the XA message, because it can subtract again the jamming message which is transmitted itself, right? So that is the basic idea of this scheme. And using this kind of ideas were used before, but not with the skilled computer forward technique, but with another technique. And what the student was able to show was that in this case we can get higher rates. So here we find, in blue you find capacity. There's some upper bounds on the sequency rate, which you find here in green. And then the technique based on the scheme that we propose here is the red curve, and you see that it goes very close to the upper bounds which was derived in earlier work. And the other two curves that you see are also making use of similar techniques with this cooperative jamming and trusted relays and things like that, but then with other techniques that they're still computer forward. Here we have that we also considered scenarios with different values of H1 and H2. Here we took the value of H2 larger, and here the value of H1 was larger. Okay, so that brings us to the conclusions, which will be very brief. So computer performance seems to be a promising technique with possible benefits with respect to throughput, energy efficiency, and security, and maybe other things. You also notice I choose my words carefully, right? Promising, possible. I've shown you some theoretical possibilities. There are also now some startup companies doing work in this area. Some more practical work has been done, especially for network coding as such. There has already been quite some test beds also, and also some first projects. For physical layer network coding, there's of course a newer techniques. These things are lagging behind a little bit. So I don't want to claim that this is the way for the future. I just indicate like this. There are promising concepts in here which could be exploited in future techniques, but there are still some things, of course, like synchronization, like all these extra processing, which need to be taken into account. Yes, so this is what I would like to tell you. Thank you for your attention.
Thank you, Jos. So who has a question? Question? Yes.
You have a linear combination of the incoming packets, right?
Yes.
And the reason for that is probably that it's easy to use error-correcting coding techniques, like with Solomon codes, to decode messages.
Yeah.
But what happens if you take a nonlinear combination?
Sorry?
A nonlinear combination. Is there any work done in that?
With network coding as such, there have been results showing that linear can always do the job, actually.
Better than nonlinear?
That if you take nonlinear combinations of these messages, that it will not give you any benefit to go to nonlinear.
Of course, in a way, it's like an access channel where you have an XOR operation, or you have an access channel where you have an OR operation. And the OR operation gives you a higher capacity. So it's strange that if you do the coding part, that exclusive OR would give you the same result as the OR.
Yeah. As far as my knowledge goes, there have been results that with linear network coding, you can achieve the same.
Yes, I think that the multi-access capacity is almost a factor of 2 higher than the exclusive OR capacity.
So I had a similar question. So you look at codes, strategies, but you can also approach the problem from channel theory. So what are the capacity regions for the different? So did you also look at that? It's more or less the same question.
Now, we did not look at that, but other work, there is work on that, but we did not take it into consideration.
And another question would be that if you do the feedback, you do compression on the feedback. You don't have to send just a combination, but you can maybe do a compression on the data and send and have an improved.
There's certainly possibilities.
So it also looks like a two-way channel.
Yeah.
And that means that you can
Use the information that you get, and you don't have to send everything back.
Yeah.
So are there more questions? Well, in that case, I think I should say thank you, Jos. And give Okay, then now we have a break, 15 minutes, I guess. Short break. And we start again at 3 o'clock. Zat er in dezelfde groep van?
Ja.
Wordt het zelfs als je feedback hebt. Precies wat ik wil vragen.
Ja. Ja, dat zijn de basics. Your founder too. Get it door?
Yeah, I assume so.
It has a practical impact that's kind of different than what that theory says. So, moving on to multi-user channels. Sorry, it's kind of a bit of a busy slide. Okay, so we have the broadcast channel here, and this is the multiple access channel and the broadcast channel. Okay, these are well known, well studied by now. We've learned some very important things from these models. We've learned, for example, that they're all essentially the same capacity, with it, as long as you normalize the same total transmit power. We've learned even very early on that successive interference cancellation is an optimal receiving strategy. For example, here or each of these guys, to cancel out interference, just decode one and then decode the other. This is actually optimal. Okay. And one really interesting thing we learned is that if you do feedback to get information at the transmitter, then you can actually orthogonalize the channel, so not go to all this trouble of interference cancellation, which is hard if you have a lot of users here. And you can then orthogonalize and do quote-unquote good resource allocation, which is how LTE, for example, works, and that this is actually optimal. Okay? It doesn't improve the capacity versus not doing feedback, but it saves great complexity. Again. Okay, so this is, for example, why LTE does an orthogonal allocation with good resource allocation. However, some of these things still are very limited. You can see there's no interference here, by what I call external interference, which means this is just like a single cell, or two guys in a cell transmitting to a base station with nothing else around it, which of course is not how real wireless systems work. And similarly, the interference cancellation is only for self-interference around these. Okay, and one example failure is that if you're just looking at these results, you can't understand, it's impossible to understand why CDMA was actually better for cellular voice than TDMA, FDMA, or some other information theoretic. Okay, I just said the opposite. Okay, so if we move on to network information theory, by which I mean not a centralized setup, but rather multiple nodes trying to communicate with each other, this gets much worse because we have intense combinatorics. Okay, so I spent a lot of time actually looking at these problems. Someone was mentioning funding. It's all about funding, right? So we looked at this for 5 years because we got $7 million to do so from DARPA. DARPA actually had been building these ad hoc networks for 30, 40 years, right? They're really interested in this. The U.S. military, so when they drop a bunch of soldiers in some godforsaken country without infrastructure, they can just set up their own network and communicate to each other, and then eventually backhaul up to a satellite or something. And they've been trying to build these for a long time, and they basically just don't work. And they've sunk billions and billions of dollars into this. And so a DARPA manager said, well, why don't we invest $13 million in basic research, get a bunch of information theorists together, and figure out, if there's some fundamental limits here. You can say we failed in one sense, but I think we convinced ourselves and perhaps others that this is essentially an unsolvable problem. Okay, even the 4-node network, we don't know the capacity of. Right? Even a 3-node network. Okay, and the main reason is the combinatorics are just very intense, and so everything's coupled. So if one guy transmits to this guy, then it affects, the channels to every other guy. Okay? And so there's a lot of coupling. And, so there's an impressive body of knowledge in this area. It's not to say that there isn't. There's this lovely book by Abbas El-Gamal and Young-Han Kim that was published that I think, really is an encyclopedia. There's been a lot of work since then, particularly on interference channels. There's been a lot of progress. There's been a lot of work on base station cooperation, but I'm sad to report that none of this stuff basically works in practice. Okay? Why is this? Okay, and what lessons can be applied towards future applications of information theory? Okay, so one of the first big problems in network information theory is that to do anything optimal. Okay, so we looked at feedback, for example, in the simple wireless channel or in the broadcasting map. Well, feedback in a network, if you have 20 nodes, ideally you'd want them all to know everything about the other 19 nodes. Okay? So this is a huge amount of feedback, right? This grows as k squared in terms of the number of channels you have to have between them, right? So you have k nodes, you have k squared channels between them. And so most IT-based approaches completely ignore this. So this is like kind of a big problem for network IT. An example here is interference alignment, a major breakthrough by Syed and his student Yvette. Actually, this was part of the DARPA project. This is one thing we could point to DARPA that they got their money's worth because he developed this result. He was on my team. But you understand this very simply. This has a gain versus orthogonality of about k over 2. So you have k users, say k is 100. This has a gain of 50. Okay, but the overhead scales is k squared. Okay, and there's been work since then that brings down this overhead somehow, and we try to. But this is like kind of fundamental problem. Okay, so another one, as I mentioned, ad hoc networks. We've thought about this problem quite a bit, and it's, in my opinion, just impossible to use Shannon type techniques to compute the capacity here due to the confidence works, the complexity and the coupled nature of the interference, and also really the only serious tool we have for these is cut set bounds, and these are very loose for large numbers of nodes. Okay. And one interesting thing we went to the military is that their networks are using, in some cases, 99.9% of the data traffic. So if you look at 99% of the bits in the air, 99% or even more are just for overhead. Okay, setting up, maintaining routes, figuring out where everyone is, obtaining synchronization, sending ACKs so you know which packets actually got delivered or not. I mean, this is hard stuff. Okay, and information theory doesn't really have much to say about any of this. At least currently. So we chronicled a lot of these frustrations in this paper that we wrote. And so I think the key point here is, this is a talk about the future, not the past, but I think we have to learn some of the, think about what we've done in the past to try to understand what to do in the future. And I think the key point is we have to develop models and tools that are appropriate to the problem, rather than just, taking, all of Shannon's great ideas for the additive white galaxy noise channel or for, compression and trying to apply them for some other really hard problem. Okay, and just hoping they work because it worked before. Okay. So I'll talk now about a few recent successes that I've found inspiring. The first one is this finite block length coding. People have been working on this since Shannon himself. And Gallagher, developed this concept of error exponents. And so this is important, particularly these days. Internet of Things is one of the new big buzzwords. The idea is that you'll have not just people sending videos and data around, but we'll have billions and billions of devices sending small amounts of information. Okay, so having short packets is important. Also these hefty overhead messages that I was just talking about for ad hoc networks. And so in this regime, we don't have infinite block length anymore, or vanishing air probability, as Shannon envisioned in his famous formula. And they found this very beautiful formula, which shows that the maximum achievable rate is capacity minus some value. So in this value goes to 0 as the block length goes to infinity, as you'd expect, and also goes to 0 as the air probability increases. Okay. But basically, you pay a penalty versus capacity depending on what air probability you actually want and the block length you want. And this is this shaping parameter. Okay. Really neat paper. It applies. Many of you have read it and followed some of Yuri's work since then. He's now a professor at MIT. We tried to hire him at UT and failed. But this really opened up a promising new approach to kind of thinking about short packet communication, thinking about error correction coding. So, this usually just came from, rethinking, again, Shannon's original result and just trying to go back to first principles. And then, it's very interesting that this is a Gaussian CCF. So, Gaussian, it still shows up in this. And so, they show this is very accurate. A second one that I really liked is looking at distributed storage. So cloud computing is all the rage. People are now storing information not in just a single device, but across the whole network. And the idea is to have massive fault tolerance and then quick fetching of information. So Facebook, for example, when you do update your status, doesn't just store this in some server at their corporate headquarters in Silicon Valley, but they rather farm it out around the country or even the world to many different data centers. So how many times do you have to store this information to make sure that you never lose it? We have to, for example, what they use is they break anything into 10 files, and then they store it on 14 servers. Okay, they store a portion of that file on 14 different servers, and the requirements need to be able to simultaneously lose 4 of the 14, which never is going to happen. All right, this is basically their definition of never. But the thing is that when you do lose a server, okay, so one goes out, the CPU breaks, whatever, or there's a read error, corruption, anything, you want to be able to reconstruct the lost data with minimal communication. So you don't want to have all 14 servers read the file, then rebuild the whole structure, and then restore it. Okay? Here's just sort of a visual example of what we're talking about. So we've broken this file. Here we use just a kind of standard 14.4 erasure code to create 4 parity packets. So basically, it's like a network coding concept. You have these 10 guys that you've broken it into, and then you form 4 parity blocks that are linear combinations of these, independent linear combinations. Okay. All right, and with this, we can lose any 4 of these at a time and still replace all 4. So you can lose 4 of the data ones, you can lose 2 of the parity, it doesn't matter. You can replace up to 4. Okay. So let's see how this works very briefly. All right, so if you have a failure, let's say you lose block 3. This by the way, are stolen with permission from my colleague, E.T. Alex Demakis. And do we want to repair it as, say, 3 parts? Okay, so how do we create this when we've lost it? So, the naive approach would be that you would, read essentially the 9 that you hadn't lost, and then read one of the parities, and then do a reverse engineering since this is a linear combination of all these, subtract out the 9 ones you know, and then you find out the third, right, using the formula that created PG. This could be, for example, an XOR of all of them, or an XOR, you can have like 2 times or 3 times to get the XOR. Okay, so you do 2 times various different ones and create linear combination. Okay, so this requires a lot of reads and communication, and again, these could be stretched out over the whole U.S. And so this seems inefficient because it's a factor of k times more than we need. Okay, so Alex, we used a grad student at Berkeley, showed that in fact this is the formula, and it's quite a bit less. So for the Facebook example, instead of I think they use B equals 640 megs is the kind of standard approach that breaks into 10 of 64 megs each. This formula comes out to something like 200 megs. So you save over a factor of 3 in terms of reads and communication. Okay? And again, I know Alex very well. He's also a close friend of mine, and a very good poker player, as it turns out. And just kind of trying to adapt it to a new problem by just talking to people outside our field, you can actually come up with fairly straightforward things that have massive impact that haven't been done before. Okay, third one. This is also stolen from my colleague Hisham El Gamal. And I really like this work. This hasn't won any Best Paper Awards yet, but I think it's very interesting. And it's a key observation, which is totally correct, which is that wireless networks these days, we hear all about how we don't have enough capacity. At least this is like the huge thing in most places. I'm sure you feel the same way here. And really the only way we know right now that works well to increase capacity of a network is to add more infrastructure. Okay? You add more base stations, you add better fiber optics or better backhaul to them, and this costs money. So essentially adding capacity to networks costs money. So we're money limited, not really capacity limited. Okay, and I'll talk a bit more about this tomorrow as far as densification. Okay, so what we do is we people get really mad when their cell phones don't work, right? When you can't, you're on Google Maps and all of a sudden you can't load the new map. I mean, this is, and so we massively over-provision supply of capacity to deal with these peaks. So you have a peak here, there's well-known times of day where you have peaks, and the peaks occur in space, semi-predictable. Like for example, at 2:30 p.m. or 3 p.m. around a high school, you're going to have a huge surge in demand. Everyone's leaving, doing whatever, right? But you have these huge surges, and you have to actually provision the supply way high, even though most of the time there's not that much demand. So you have all this wasted capacity most of the time. And I can tell you, I've seen lots of data, as I work with Verizon and AT&T on these kinds of things. The network, on average, is about 10% utilized. Okay? Often less. So most of the capacity is just sitting there idle. So it'd be awesome if we could somehow move this demand elsewhere. Now, you can't move it later because that makes the customers mad, right? If they can't load the map or do the Facebook update for an hour, then they don't like that. So why don't you move it before? Okay? Very simple idea, right? So just remove the causality constraint. Okay, and we can do this in theory by caching or prefetching. So you basically store this stuff very close to the source, or even actually put it onto their phone. So, for example, you learn. This is kind of a combination of big data type of ideas and information theory. So you learn that this person's a sports fan. Okay, they often are going to get out do something, and they're going to open their ESPN app or sports app and watch. I guess we're in South Africa. They're going to watch the rugby. Rugby World Cup's coming up. All right, people are going to watch the Rugby World Cup highlights. So you put that on their phone when they're in a place where there's spare capacity. And not only do you put it there, but you train them to use that. So, for example, when they open up their ESPN app, the first thing that comes up is the cache content. Well, they can scroll down and do something else that's not cached, but you put the cache content first. So there's ways of training people to actually use this stuff. Okay? And so what does this have to do with information theory? Well, in a way, it's about, like I said, relaxing the causality constraint to coding, and actually it can be thought of as a means of widening the timescale for coding. Okay? And two of these papers, which I'll point to, this one by Hesham, and then this one by Mada Ali and Urs, who are at Bell Labs in New Jersey, on fundamental limits of caching. These are two nice representative papers that really get at the fundamentals of this caching problem. Again, both information theoretic approaches in our transactions. And I think what's really cool about what Hesham's doing is he actually has a successful startup that's doing this. In many countries in the world, he's working with providers. The U.S. ones are generally very hard to work with, so he's doing a lot of work in the Middle East and Asia. But they actually have been showing that they've been able to achieve routinely 50% caching. So in other words, you cache the stuff on people's phones, and then over half the stuff you cache will get actually viewed. Okay? And in many cases, they get above 100%. What does that mean? What does above 100% caching hit rate mean? If you have a daughter like mine, you know that she watches the same video over and over again, or listens to the same song over and over again. That means you watch it more than once. Right? So not only do you have to not communicate it during this crunch time, you communicate it in an off-peak time, and then they watch it repeatedly. So you're just saving each time you're saving on the network. They've been able to really show massive gains from this. Very exciting, I think. And, I don't know if any of you know Hesham, but he's a coding theorist, and that's his training. He's an information theorist as good as they come. Okay, so the last 10 or 15 minutes here, we'll proceed with caution to new areas, and indeed, Shannon warned about this as early as 1956, and this paper that's sometimes called Shannon Gets Snarky. It's a one-pager that appeared in the Transactions on Information Theory. It's called The Bandwagon, and it's fun. It's a fun little read, but he points out this. Just a couple of quotes here. He already points out that people are being applying this. By the way, this is before, if I'm not mistaken, this is actually before DNA structure was even discovered by Crick and Watson, but they were already applying it to biology. So I think he already warns that you have to be very careful applying these results. You can't just, he developed these for the added white gas noise channel. He thought about it just in terms of as a communication engineer, and they should really be careful about applying them to other areas. Okay, and I think we can see, I'm sorry, I forgot the last name, esteemed Vice President of IEEE. There's 75,000 citations. If you look at the recent ones, they're almost all outside of electrical engineering. Okay, they're all from bio, psychology. I mean, if you can actually just go to Google Scholar and look at the recent citations, almost none of them are even from engineering. So everyone's applying, it's just mindless, it's not necessarily mindlessly, but they're not heeding Shannon's warning necessarily. And so I just want to talk specifically about life science. Because I think life science is probably the least mature of any of the sciences, and there's great hope that this will be kind of the century of life science, where we'll learn how to develop genetic treatments for cancer, and all these other wonderful things, cures for Parkinson's and Alzheimer's, and stem cell research, et cetera, et cetera. Okay? And so there's a lot of applications in life science, but two that particularly appear right for information theory are genomics and neuroscience, okay, as I mentioned earlier. And the key challenge to all of these is developing, again, these abstractions that are, we can actually do something with. So it's got to be simple enough that we can actually do math, but complex enough that it actually, is empirically justified and close enough to reality. Okay? And it's pretty clear we can't just apply the same stuff Shannon came up with 60, 70 years ago and expect it to work. We have to develop new approaches. Okay? And this is hard. Okay? It's already, I'll just point out some of the areas where information theory is already having an impact in bioinformatics and genomics. And as I mentioned, I got very interested in this. I first got interested in this, you see the name Viterbi here. So he is one of the founders of Qualcomm, and of course the Viterbi algorithm for decoding convolutional codes. Turns out this is actually how they do state estimation in DNA sequencing. And one of my best friends from college, one of the smartest people actually I've ever met, got his PhD from Berkeley in theoretical chemistry at age 23, and majored in not only chemistry but math, computer science, and music in college, graduated when he was 18. I was hanging out with him on a ski trip. He's like, yeah, we're actually using this Viterbi stuff to decode. He works for now a DNA sequencing company in the Bay Area. And then he's like, yeah, it's really interesting. We're using all this information theory stuff. I've been reading Shannon's papers, and I just found this fascinating. So I talked to him a bit more about it. And that's how I initially got interested in this. And so it turns out there's and you'll see his name, John Sorensen, is one of the external contributors. And so there's all these things that are being used from our field in DNA sequencing in particular. Graphic models is one. But it all comes down to information, right? Because genes are nothing but just base 4 storage. Right? And another big one is trying to do compression of genetic information for storage. As we sequence all these genomes, it's a huge amount of information. Trying to compress it, compress the right things. Again, lossy compression won't really get it done. We need to. Most of the genomes in the body are useless. Actually, they're just kind of they're late for legacy reasons. They don't actually do anything. So figuring out what those are, and figuring out good compressors, another one. And of course, some of the well-known statistical methods for us, like hypothesis testing and so on, are very important too. A good starting point, I think, for those of you who might be curious, is to look at this. There's a paper by this guy, Christophe Adamy, and he has a few papers, a number of papers on this, but he has a kind of a recent survey from 2012 called The Use of Information Theory in Evolutionary Biology. And this is just an example figure from one of his papers. And what this shows is basically, I thought this was appropriate since we're in Africa, next to Kruger National Park. There's all these different animals here, and basically the amount of entropy of the proteins in the body. And this entropy is measured in a unit called MERS, which I've never heard of before. And MERS is a base 20 log unit. Again, the reason they use base 20 is because that's the number of amino acids that can make up a protein. So essentially, one MER then is essentially, so the maximum entropy for a given state in the protein molecule. But what I found interesting reading through his paper and a bunch of the other related work is this is all chapter 1 of Kruger and Thomas stuff. So imagine if information theorists really got involved and learned, became fluent in genomics. I think we could make a very large impact there because we've gotten much deeper and understand much more some of the tools that could actually be used, even beyond anything in Kruger and Thomas, much less chapter 1. Okay, so I think this is a field that I hope, it's hard to learn a new field, but if I was a grad student today, I would, in information theory, I would try to almost have a dual, focus in some other area. Like I would just at least take like 5 genomics classes and maybe get an advisor. I think this is a really ripe area. I didn't have time. I decided to cover neuroscience, but I have another friend who's an external collaborator who I know from Stanford days, who did information theory and started wireless companies and just finished his postdoc. He's becoming a faculty member in neuroscience. And he also pointed out all these intersections between information theory and neuroscience. And in fact, his PhD was largely on this. So I think there's just tons of interesting ways to apply information theory to other fields. Okay. So in conclusion, I think we should all have the goal of letting information theory be a field in its own right, not just a subfield of E. I mean, of course, it's a little tricky since we all have to have faculty appointments or get PhDs in something. It's typically an EE, but I mean, I think right now the only other departments that I'm aware of really having information theorists are some computer science departments do, maybe some statistics departments. But it'd be great to, if not entire departments in information theory, but just having it viewed as really its own field that has intersections